In today's lesson, we're going to continue with our approximation of the area underneath the curve. So what we're doing is called Riemann sums. Finding the area under the curve with rectangles is called a Riemann sum. Okay. So we're considering the graph that is underneath y equals e to the x, e to the minus x from 0 to 2. So this graph is an exponential decaying function that looks something like this. So here's x equals 0 and x equals 2. And the first exercise is to calculate R10. So R10 would be to split up the area underneath the curve into 10 equal subdivisions, and we want to use the right approximation. So your first rectangle, you would use the right corner to form the height. All right, so we don't really need the picture in order to do these, but the picture is helpful for figuring out the right formula. All right, so B is equal to 2, A is equal to 0, N is equal to 10. So delta x would be the width of each subdivision, and that would be B minus A divided by N. So that's equal to 2 minus 0 divided by 10, which is 1/5, or 0.2. Okay, so if delta x is 0.2, then this first subdivision is 0.2, that'll be 0.4, 0.6, and the very end would be 2. So computing the area, it would be delta x times the height of the first subdivision point plus the height of the second one, where this one would be x1 right here. That would be x2. This would be x of n, or x of 10. So we would go from x1 to f of x of 10. All right, so let me erase this extra delta x over here. Okay. All right, so plugging in, so this would be 0.2. So x1 would be 0.2. So that would be e to the negative 0.2 plus e to the negative 0.4 plus e to the negative 0.6, all the way up until we get to e to the negative 1.8 and e to the negative 2. All right, so this would be the R10 approximation of the area underneath the curve. All right, part B is to find the midpoint approximation. So let me draw this a little bit bigger so I can explain the midpoint. So let's look at a blow up of this. And suppose we have xi, and then the next subdivision point, xi plus 1. So instead of using the left or the right to determine the height, we can use the midpoint. So this midpoint right here would be xi plus xi plus 1 over 2. It would be the average of the left and the right x values. So we would form the height of the rectangle by plugging in the midpoint of the subinterval. Okay, so keeping that in mind, our subdivision points will be x0, which is 0, x1, which is 0.2, x2, which is 0.4, up until we get to x10, which is 2. So instead of using these numbers to determine the height, what we would do is take the midpoint of each of these intervals. So we would say x1 bar would be the average of 0 and 0.2, which would be 0.1. x2 bar would be the average of 0.2 and 0.4, which would be 0.3. So now we just keep shifting over by delta x, which is 0.2, and we're landing on the midpoints. All right, so let's put this all together and try to write out the M10 midpoint approximation. Okay, so let's draw the graph of e to the minus x. And let's look at our subdivision points. So x0, which is 0. I'll draw it a little bigger. x1, which is 0.2. x2, which is 0.4. And we would end at x10, which is 2. Okay, so what we need are the x bars. The x bars would be the middle of each interval. So this first subdivision would be 0.1, 0.3, 0.5, and we would end at 0.9. So draw like a dotted line until you hit the graph from your midpoint, and use that to make the height of the rectangle. Okay, so doing the calculation, just like we did before with the right approximation, except now we simply use the midpoint as the height. So M10 would be delta x times f of x1 bar plus f of x2 bar to f of x10 bar. So that's 0.2 So e to the negative 0.1 plus e to the negative 0.3 plus e to the negative 0.5 up until e to the negative 1.9. Notice we're just shifting to the right by 0.2. All right, so that is how you approximate using the midpoint and the right Riemann sum. Okay. The odometer of a car is broken. In order to estimate the distance traveled over a 30-second time interval, we take the time every 5 seconds and we measure the velocity at that time. So time equals 0, we're going 25 feet per second. Time equals 5, we're going 31 feet per second. Now, using the velocity data, let's see if we can estimate the distance traveled over a 30-second time interval. All right, so let's take a look at the textbook, page 367, 368. So in the textbook version, they first start out with miles per hour. You're looking at your speedometer. And then they convert that to feet per second. So this first step is not important. So what we're going to do is try to calculate the distance traveled every 5 seconds and essentially add them up. So think about, what does the area of each rectangle represent? Okay. So let's plot these points and calculate what the area of each box would represent. So time equals 0, so this is time in seconds versus velocity in feet per second. So time equals 0, we're going 25. So for the first 5 seconds, from 0 to 5, let's assume that we're going at a constant velocity of 25 feet per second. And then from 5 seconds to 10 seconds, well, let's assume that we're going 31 feet per second. So this is, sorry, I think I mislabeled that. Okay, so from 5 seconds to 10 seconds, the height would be 31 feet per second. And let's assume that from 10 seconds to 15 seconds, we're going 35. Okay, so let's do some of this multiplication. So let's find the areas. So the area of the first box is 5 seconds times 25 feet per second. As you can see, the seconds cancels out, and what you get is distance. So this comes out to be 125 feet. So you see the area of the first box represents how far we traveled in the first 5 seconds. Remember, average velocity is change in distance divided by the change in time. So multiplying delta t on both sides, you get delta s. So velocity times time will give you distance. So our distance has changed by 125 feet. So the area of each box represents how far you travel over the 5-second interval. So by adding up all the area of the boxes, we can get the total distance traveled over the 30 seconds. Now, the moral of this story is that as you increase the number of boxes, the approximation becomes better and better. So going back to our pictures with many rectangles, so here's what we just essentially did. We found the area underneath these boxes, and that approximates how far we went in the first 30 seconds. However, we could have taken better measurements, maybe instead of every 5 seconds, maybe every 3 seconds. And we would have calculated the distance traveled over each of these little time intervals. So what if we let the number of rectangles get infinitely many, infinitely thin? We get the true area underneath the graph. So the important thing to understand is that the distance traveled is the area under the instantaneous velocity function. Right, that's the important thing to remember. So the area underneath a velocity curve is the displacement, the change in distance traveled over that time period. So keep that in mind. Area under the velocity curve is the distance. Okay. So that was the introduction to area underneath a curve. And now we're going to get a little bit more sophisticated and introduce a very important concept called the definite integral. This is section 5.2 in the textbook. And this definite integral is one of the most useful constructs of calculus. Okay, so what is a definite integral? Well, first of all, we write it. We're introducing something to represent what we've already been doing. So the integral from a to b of f of x dx is the limit as n goes to infinity of the Riemann sum with n rectangles using the right approximation of the area underneath the curve. So instead of thinking of just the area, see, the logic is, well, this is the logic that we did. We started with some graph from A to B. And then we saw that we can make subdivisions and calculate the area using either the right approximation, the left, or the midpoint. But this process of finding the area underneath the curve, that's called we're going to represent that by the integral from a to b of f of x dx. So the area underneath the curve is defined to be the integral from a to b of f of x dx. The dx is sort of like a symbol, but it stands for the delta x that we have here. And the f of x, that's our function. A to b is where you start and stop. So the area is the integral. However, when the function goes below the x-axis and is negative, we still can do the integral. But now the area is a little strange. We have a negative area and a positive area. So when you try to do the right approximation, where if a function below the x-axis, what you get are rectangles that go negative, have negative heights. So this still makes sense when you apply this process of multiplying height times base. Height times base. It still makes sense even when you have negative heights. And that's what the definite integral is. It represents the signed area underneath a curve. When the graph is above the x-axis, it's positive area. When the graph is below the x-axis, it's negative area. All right, so let's stop here. And I don't want to get too far in this pre-recorded video. We'll continue over here next time.